if I remember. Okay. So here we have notes on nuclear uses. So, you know, little cartoon there from Cyanide and Happiness. This is kind of what we're talking about, right? So, nuclear fission. So looking at this set of notes here, we've already talked a little about fission and fusion. Today we're going to get a little bit more into the detailed process of it. And because of that, that's why we've been doing so many things that are so detailed and minutia. This is kind of what it's all been leading up to, because we're going to go through these processes here and you're going to see things, you know, if I hadn't mentioned them earlier, you wouldn't have seen them until now. So, the definition of nuclear fission is to split an atom, and the result is either a nuclear reaction or radioactive decay. In 1938, two Germans by the names of Otto Hahn and Fritz Strassmann discovered that when the uranium-235 isotope was bombarded with neutrons, it absorbed them and split into lighter atoms and gave off more energy. There's a nice video there, which I might show at the end of class today, or y'all can watch on your own, about this whole thing. I do want to make mention that most of the time when I talk about scientists doing work, I don't pay too much attention to the dates, because I mean, dates are just dates. But it should be noted that that date's actually pretty important. Why? Why is 1938 important?
World War II.
When did World War II start?
35.
Well, sometime in the 1930s. Okay. Well, at any rate, World War II, who was decided to be the bad guy in World War II?
Germany.
Not just Germany, but Nazi Germany.
Okay.
It's important to know that they were Nazis, because Nazis are bad. No, Otto Hahn and Fritz Strassmann were not Nazis as far as I know, maybe they were. But they were definitely Germans. And as a result, what happened is these two Germans were doing experiments. Now it's interesting because it says, you know, the uranium-235 isotope. So first of all, you should know a couple of things about that. Uranium is not normally uranium-235. Uranium-235 actually only makes up 0.7% of naturally occurring uranium. So what the heck were they firing neutrons at some random isotope of uranium for? What were they hoping to find? Well, it's actually something that was started by Rutherford back in his gold foil experiment. Remember, Rutherford was firing things at gold foil, and he happened to see that some things reflected off of stuff, but most of the time the things just passed it straight through, which indicated that there was a very hard core to this material, right? That's what indicated that the atom had a nucleus. But the whole point, what I want you guys to see is that, like, scientists don't just do this like randomly. They basically just go down the table. And so the fact that they are firing neutrons at stuff, they were firing neutrons at a lot of things, okay? They just happen to be doing uranium-235 that day. Does that make sense? Like, it's unlikely that they were expecting much of a reaction, but basically it's like, well, fire a neutron of this, fire a neutron of that, what's going on? It's important to note that that happened in 1938, because when Otto Hahn and Fritz Strassmann got their data from this, it was so bizarre and so weird they didn't know what was going on. And as a result, they had to contact some of their fellow colleagues who were not in the country anymore. For some reason, their Jewish colleagues had decided to leave Germany for some reason. And as a result, they sent it to where they were, and they were located in Switzerland. So the colleagues had moved to Switzerland, and as a result, they sent the data to Switzerland. Now, Nazi Germany would have liked them to not have sent that data, just because Nazis be Nazis. And as a result, They realized what Otto Hahn and Fritz Strassmann had done. They had forced the uranium nuclei to split. Like they had done a reaction, which, you know, people have been studying up to that point as transmutation, just, you know, the atoms splitting naturally. They realized that Otto Hahn and Fritz Strassmann were the first people to actually force it to split, right? And that is a big deal for several reasons. First of all, now it opens the door that we can start splitting atoms, you know, if we want at any time. But before this point, nobody even thought it was possible. And they kind of did it by accident. So that's very, very important to know. Because it leads to a lot of what's going to happen. Then there's also nuclear fusion. Well, here, let me go back a second. So basically what happens here is you have the uranium-235 nucleus, and you fire in one extra neutron. So that extra neutron gets absorbed by uranium-235, and for a brief time becomes uranium-236, which is super unstable. And it splits off, and I think, if I remember correctly, krypton and barium are the two daughter nuclei. And then it splits, but it also sends off usually 2 or 3 more neutrons. And that's important because if there happens to be a big chunk of this that was started by a neutron, and now you have 3 more neutrons flying out, there's a good chance those neutrons can hit another nucleus, right, and start a chain reaction. This is the process of nuclear fusion. It's where you take atoms and squish them together. This is specifically, so that one was specifically uranium-235 being split. This is hydrogen becoming helium, and this is the process that powers the sun. Nuclear fusion happens when 2 or more nuclei come together to form something heavier. And it requires very high temperatures and pressures. Fusion reaction is taking place in the sun and the stars. So with fission, it's basically as long as you can get the neutron to hit the nucleus, it's good to go. Now that's relatively difficult. It's easier said than done. But it doesn't require super high temperatures and pressures. Now, it turns out that increasing the temperature and pressure can actually increase the likelihood of neutrons hitting, but you don't necessarily need them to get going. Now, with fusion, you have to have very high pressure and temperature because essentially what you start with is 4 hydrogen atoms or 4 protons, and you mush them together to become helium. And protons don't want to be near other protons, right? Then you have that electromagnetic force that will cause them to repel. And so you're trying to mush them together, but you have to overcome that electrical force. Because again, it's just like really strong magnets. If you put them together, and they're real strong, they don't want to go together, right? But essentially, if you have them at high enough pressure, high enough temperature, you get them moving fast enough, you can just slam them together. And in reality, it still requires a bit of what we call quantum tunneling, which I'm not getting into. But essentially what happens here is you can start with 4 protons, and if we take just one part of this chain here, you can see that like the 2 protons get mushed together. Let's say you get 2 of them going fast enough. They squish together, and what happens is one of your protons becomes a neutron, and when that happens, that's beta plus decay, right? So a positron comes out right here, but then also, and this is the thing that was predicted in math before we actually detected it, another thing comes out called a neutrino, right? And so, unlike this positron here, if that positron encounters another electron, it's going to immediately annihilate and form energy. But this neutrino here is just going to come basically straight out from the reaction and not interact with anything else. Then you have the hydrogen with a neutron, which is now called deuterium. It's just an isotope of hydrogen. Then you have another proton come in, squish. That one doesn't change, it just drops some energy, so it's released as a gamma ray. And then if you do that twice, you'll get the helium-3 nucleus, right, an isotope of helium. If we mush these 2 together, then we get the helium-4 nucleus, and then 2 protons come back out. So you can kind of be like, well, I actually need 6 hydrogen atoms or 6 protons here, but you get 2 left over in your reaction. They're more like catalysts. And so that's the stuff that comes out. Now, it should be noted that according to our calculations, the process of this energy here, like from this gamma ray or from this positron, takes roughly like 10,000 years to make it to the surface of the sun, whereas neutrinos pretty much just come straight out at the speed of light. All right, so where does the sun get all of this energy? So this is a picture of the sun, and that is a picture of the Earth, and they're put to scale next to each other. This here is what we call a coronal mass ejection. It's part of the sun throwing a piece of itself into space. I show this picture because if you do the math of how much energy is coming out of the sun, you know, you take like a little sampling, okay, how much energy are we getting for this area? And if that's the same over the whole area that the sun is putting out, well then we can calculate how much energy that requires. And all of this energy is powered by E equals mc squared. Like literally mass is becoming energy. And through this process, the mass of the sun is reduced by 4 million tons per second. That's like losing 4 million elephants every second, relative to light elephants, which is mind-boggling. But that's what I'm trying to emphasize to you, that 4 million tons of mass is basically nothing compared to the Earth. Compared to the sun is less than nothing, right? The Earth is big, but the sun is just stupid. Okay? It's just so big that like it's hard to think about. So I want you guys to understand that like if you do these calculations, you get these ridiculous numbers, which aren't ridiculous compared to what's going on. But yes, the sun is getting lighter. All right, so nuclear power. There's different types of nuclear power. Obviously, there can be nuclear fission and nuclear fusion. I'm going to start with nuclear fusion because it doesn't exist, so there's less to talk about. With nuclear fusion here, this is nuclear fusion. The whole point is doing the same reaction that's occurring on the sun just here on Earth. And we can do that. The only problem is it requires such high pressures and temperatures that we have to heat up the hydrogen enough and have it under such pressure that it requires, well, a lot of energy to start it. And basically up to this point, we have not been able to get more energy out of the reaction than it took to heat everything up in the first place. So, that brings up what we call cold fusion. Now, again, it's one of those misnomers that cold fusion just really means fusion at a lower temperature, you know, not 10 million degrees. So the pros is little fuel is needed for fusion. You just need some hydrogen, so just isotopes of water, because water is H2O. And a lot of times, if you just look at the water, you'll find H by itself. And some of those H's will be deuterium, which is already, you know, one proton and one neutron. Like you can just filter the water and get the fuel. So that's pretty cool. And there's no radioactive output. Like worst thing happens if your fusion power plant turns off, it just stops making energy and maybe releases hydrogen. Just not toxic, because as I mentioned, it's already in your water. Cons, you need a lot of high temperature and pressure must be maintained, and again, right now we need more energy to start it than we've ever been able to produce it. Now there's several fusion reactors being built in Europe. There's the Tomahawk, which is already running, but again, it simply proves that we can do that. But the E-tier reactor is the one they're currently building, and it's one of those reactors that occurs over, it's one of those reactors that as they're building it, it should have been, they thought it was going to be finished in 2021, but now it's looking more like 2025. Because it's one of those scientific projects that, basically things are more expensive than they thought, and people pull out, and they don't have enough money, and blah, blah, blah. Anyways, the theory is we just haven't built a big enough reactor yet. So, maybe. Now, here's the thing about fusion in general. One of the main reasons why we don't see a whole lot of money going into fusion is because we don't know if it will ever be profitable. Like, we don't know if it'll ever be an actual energy source we can use. I mean, sure, the sun, we can tap into that, but as far as here on Earth, like, there's some calculations that show that you're just never going to be able to get more energy out, and we have to heat everything up. And then there's some calculations that are like, well, if you twist the magnetic field into this helical shape, maybe we could, and it's all this different stuff. And so it's really hard to tell if it's ever going to be viable. Because I guarantee you, if somebody could prove we could do cold fusion or do fusion and make more energy, the energy companies would be all over it. Because there is nothing that's as good as fusion. Just nothing. But the problem is we don't know if it'll ever be profitable. So a lot of companies are like, well, why should I invest money in something that may never pay off? So it's really hard to get research money for this, which is one of the reasons why it goes so slow. This is just an example. If you click on that link there, it'll take you to a video that kind of explains how this particular cold fusion reactor might work. Or, I guess it technically does work, but it doesn't produce enough power. All right, so let's go to the other end, nuclear fission. How do we get nuclear fission? Well, nuclear fission is a lot easier, and that's what our nuclear power plants are. But in order to do nuclear fission, well, you got to have enough of the right material. Because as I mentioned, uranium-235 works pretty well, but it only makes up 0.7% of natural uranium. So how do you get enough? Well, you do a process called uranium enrichment, and there's different ways to do it. Back in World War II is how they figured out, during what they call the Uranium Committee, is they figured out if you take uranium and combine it with fluorine, it makes a gas, and then you can filter the gas. But the difficulty here is you're trying to filter out uranium from uranium. You're trying to filter out uranium-235 from uranium-238. They're just different isotopes. That's important to note because there's no magnet that will pull on one more than the other. There's no chemical that will bond with one more than the other. The only difference between uranium-235 and U-238 is that U-238 is slightly heavier. I mean, yes, it's heavier, but by 3 neutrons heavier. And so they had to make a process that would separate this, and so they make uranium into a gas, like so by combining it with fluorine, and they send it through several different, generally nowadays through centrifuges. But these centrifuges have to be very, very well made, very well built, because you can't spin them at a low speed. For instance, your car, a lot of cars have what's called a tachometer, and that tells you how many times per minute, like RPMs, revolutions per minute, your engine undergoes. So if you're at like 1,000, like 1, because usually your tachometer is written as 1 times 1,000. If you're at 1,000 RPMs, that means your car is undergoing 1,000 revolutions per minute. Now that tachometer has a red line, which means if you go above that red line for too long, your car will get overheated, because basically the components are spinning so fast that they might spin themselves apart. And usually that red line's above 6,000 or 7,000 RPMs for normal cars. Now, fancy race cars, like Formula One cars, their stuff is designed to run at a higher RPM, and so they can run at like 15 or 16,000 RPMs, whereas your car would definitely explode at that. But the whole deal is like, why can't my car do that? Well, it's just the stuff that makes up your car's engine is not as well made as the stuff that makes up a race car engine. Sure, if you went and bought that stuff, put it in your car, it would be fine. But there's a reason why it costs more. You're with me? So these centrifuges that end up being used in different places, like there's a picture of the K-25 plant that we used to have here in America, in Oak Ridge, Tennessee. that they have to do these things that spin at least 10,000, if not, closer to 100,000 RPMs. And so these things have to be made extremely well. And when I say extremely well, I'm not really talking about, it's a different material. I mean, generally it is, but basically you have to make it so it's very well balanced because it's spinning. And if your little shaft isn't, balanced, there's a couple more atoms on this side than that side, and you start to spin it that fast, it'll be uneven and it'll start to wobble and it'll break. Which is why it's very difficult to enrich uranium. And it doesn't typically happen on a very small scale. Now we still have a plant that does it. There's one in Ohio that does it, but these centrifuges take a lot of energy and they take up a lot of space. So it's very obvious when somebody starts to try to enrich uranium, and when I say somebody, I'm talking about countries. And it's one of those things that you can hear in the news, like a few years ago we talked about the nuclear program in Iran, and people were like, oh, Iran's making nukes, blah, blah. It's like, well, how do you know? Well, it turns out that Iran had built this giant building, and then if you watch like satellite photos, like you come back to like, or if you look there now, it's just a big pile of sand. But if you look at previous satellite photos, you can see that like they built a building and then covered it with sand. And so it's very obvious, like, you buried a whole building for a reason. And they're like, there's no building there. There never was. Like, okay. Yes. And so I point out Iran, they're not the only ones, and anyway, I'm not going to digress into that. My point is this is not a small thing, and it's very obvious when people do it. So it makes me chuckle when people are like, you gonna build a nuclear bomb? And I'm like, how? What do you think I'm doing in my garage? Like, anyways, that's what the workshop's for. So here, it turns out though, there's another process. If you take uranium-238 and you hit it with a neutron, bombard it with neutrons, it actually bumps up to uranium-235. And then what they found out was uranium-239. The uranium-239 ends up usually undergoing a half-life about 23.5 minutes. It undergoes beta decay, minus decay specifically, and will decay to neptunium-93. And then if you let that sit long enough, it undergoes another beta decay to become plutonium. And plutonium is another thing, just like uranium-235, they can be reacted upon pretty easily. It's not the same process, but similar. And so they found this pretty quickly, which is why in World War II, when they built the first atomic bomb, the Gadget, that was uranium powered, and they built actually 3 more bombs. They built the test one, the Gadget, and then they built Fat Man and Little Boy, which you've heard of, and then a 4th bomb that was actually never used. But some of them were powered by uranium and some were powered by plutonium, because literally, like when they gave this material to the scientists working at Los Alamos, it was literally all that we had. So yeah, that's why we ended up with 2 different types, because they weren't sure one or the other was going to work. So anyways, so atomic bombs. So thermonuclear fusion has already been used for war purposes. So we have fission and fusion. So let me say here, so we have an atomic bomb, or an A bomb for short, and then we have a hydrogen bomb, or an H bomb. So nuclear fission is what's responsible for an atomic bomb. So like the Fat Man, Little Boy that were dropped on Japan, and the Gadget that was made in the desert, detonated here in New Mexico, those are all atomic bombs. But it turns out the problem with nuclear fusion, remember I said you have to get the pressure and temperature hot enough to make it occur? Turns out if you use an atomic bomb, you can get really high pressure and temperature. So what's interesting here is we can use, before I say it, do you guys know how a car works? Like when in the morning, when you go to start a car, you just push a button, turn a key, right? When that happens, you send current to your starter. The starter grabs the big flywheel on your car and just gives it a big turn, okay? And basically you can start the engine moving like that, and as the engine starts to move, you know, when one of your pistons gets to top dead center on its power stroke, it ignites that cylinder and then it fires, thus starting the whole process of the engine actually running itself. Does that make sense? So whenever you turn the key or push the button, it's just a little bump to get your car started. Now that little bump is actually a significant amount of current from your battery, which is why car batteries are so big, even if you don't have a hybrid. But that amount of energy that's needed is far smaller than the energy put out by the engine itself. Does that make sense? I want to say that because you need something to start your car, literally this starter. Well, in a hydrogen bomb, or sorry, let's go to atomic bomb. In an atomic bomb, they actually use a small explosion, like a C4 or some type of plastic explosive usually, to start those neutrons moving to start your nuclear fission process. So a small explosion from something like C4 starts our atomic bomb on its explosion. But again, it's a small explosion that it creates a larger one, right? For a hydrogen bomb, that small explosion that starts it is an atomic bomb. I say this because, you know, you're probably never going to see one in real life, hopefully. And the whole deal is, it's hard to know the difference between these two. And let's just say that a hydrogen bomb and an atomic bomb really aren't on the same scales. Just like, you know, classic explosive makes things explode, but not on the same scale as an atomic bomb, right? Like C4 will blow off a door. It will not blow off the city. All right, so it's hard to look at the difference here. So there's several links here. Hopefully they work. Although we definitely found one earlier that didn't work. Y'all can click on these, and they're different links. Some of them are simulations. Like NuGet's a fun one, where you can just pull up a map of Google Earth and just nuke random things. And see, oh, what kind of damage does that do? We might do that later. There's nuclear triggers, nuclear weapons, modern nuclear yield. It kind of just shows you like the difference between like the old bombs and the new bombs. You might be disturbed in some of these. And then nuclear detonation time lapse. The nuclear detonation time lapse is really interesting, especially if you think that only 3 nuclear bombs have ever been detonated. You would be wrong. Let me take a quick poll. How many do y'all think have been detonated? Keep in mind, it's illegal for anybody to detonate atomic bombs right now.
30, everybody.
30? Huh?
Over like 50.
100.
100.
How many nuclear bombs have been detonated on Earth? Well, not just us, but everybody together.
Probably like 300.
Where did you get that 200 from?
It's over 2,000.
Oh, wait, what?
I was
And if you, we might watch this video later, but it shows you exactly where all of them have been detonated, because as we mentioned earlier, they have very unique signatures. And when things like neutrinos are made, they don't get blocked by pretty much anything. So,
What kind of damage does a beach bomb do?
depends on where you put it. Now, most of the time when we test these things, it's out in the desert, or it's places we don't care about, like the desert,
Alaska.
the ocean, space, like places we don't care about.
Wyoming.
Canada.
Who's doing the most bombs?
Oh, us.
Oh,
We
yeah.
never would.
Oh, besides us.
Russia, whatever you want. So nuclear fallout. So after nuclear blast, there will be radioactive particles that get forced into the atmosphere and eventually fall or get carried by wind and spread. Because the thing is, whenever you detonate these things, you know, if you're using radioactive isotopes to make the bomb, not all of them get used. So for instance, the one that was dropped on Hiroshima, I believe that was a uranium bomb, and only about 1 kilogram of mass was converted to energy in that case. The rest of the bomb, the rest of the radioactive material just got spread out over the whole city. That's actually a benefit for using hydrogen bombs because they don't really leave radioactive waste behind. Because you know it's green. So it depends on the proximity to the blast and length of time exposed. These fission byproducts, the effects will vary. I'm not going to click on these. Feel free to click at them. If I remember correctly, those can be relatively traumatizing. So this is stuff from like the CDC, the Center for Disease Control, for like acute radiation syndrome and radiation contamination versus exposure. But again, these are actual pictures of generally people that have been exposed to radioactivity, especially after what we did in World War II. And that's one of the things I think is really hilarious about world politics in general.
Okay, I was supposed to.
And the thing I find hilarious about world politics is how like a lot of countries will be like, oh no, we're tough, we'll kill you or whatever. It's like, if you literally look at history, there's only been one country in the history of the planet that has actually nuked other people. That's us. And I think it's really funny because people are like, oh, well, I'll kill you. It's like, yeah, but we have a history of doing really horrible things and everybody seems to forget. And it's just like, but we do that occasionally, so maybe not forget it. Anyways. I think that's it for this set of notes. Next class we'll focus more on what we did essentially after World War II. So earlier I noted about the 1938 thing. The reason why that was so important was because once people realized, like, hey, we can force atoms to split, it turns out that someone had already figured out how to make an atomic bomb. He had actually already figured it out, and he was living in Britain at the time, and he had it patented. Like, he patented the world's first atomic bomb. And that was actually back in 1932. So a patent existed 6 years before they figured out how to split an atom. And so when people saw, like, oh, they split an atom, they went, oh, wait, who learned to split an atom? Germany? Oh. A lot of people realize, like, this dude figured out how to make an atomic bomb just walking down the street. Literally, he was walking down the street when he was like, oh, if you could just figure out something to start this thing and you get enough of it at the same spot, it'll just start this chain reaction, makes a bomb. And then, 6 years later in Germany, Nazi Germany, they figured out how to start that. And so some people got relatively concerned. And the guy that actually, I think his name was Leo Szilard, he actually got very concerned about it. And he was just like, he had also left Nazi Germany for various reasons, obviously. And he was very concerned about what Nazi Germany might be doing with that information. And so he talked to his friend, who didn't live in England at the time, his friend who had also left Nazi Germany, his friend Albert Einstein, who lived in America at the time. He went and talked to Albert Einstein and was like, yo, have you heard about all this stuff? And Albert Einstein had not. And he started thinking about it going, you might be right about the Nazis and this whole atomic bomb thing. And so Albert Einstein wrote a letter to the President of the United States explaining these things. And that's why Leo Szilard had Einstein write the letter, because, let's face it, do you know who Leo Szilard is?
No.
No. And chances are, if he wrote a letter to the President, the President wouldn't read it. Or wouldn't even take it seriously. And so that's why he had to get his friend Albert to write a letter for him. And when the President read that letter, he also became a little concerned, which is what started the whole Uranium Committee and then the Manhattan Project. Now it turns out the whole point is Germany might be working on atomic bombs, so we need to get it first. That has done so much scientific research, basically in the course of the Manhattan Project, over the Manhattan Project was really only about 2 years, but the Uranium Committee was like 2 years, so you can call it like 4 to 5 years for this whole thing. the amount of research that was done in that time is equivalent to like 100 years of normal research. That basically we put a bunch of the smartest people we could find, who basically weren't Nazis, and put them in a room and said, work on this. And so we gave them a ton of money and a ton of research got done very quickly. Which is why pretty much all of our stuff, you know, we talk about quantum mechanics and general relativity, like almost all of the stuff was done through the Manhattan Project because we put so many people together who A, were super smart, but also B, we gave them a bunch of money so they could do all of this research and figure this stuff out. Now,
If we could just figure out a way to use cold fusion.
there you
It's
go.
so easy.
So, anyways, when we look at the next set of notes, we'll basically continue and we'll look at things that happened after the war. But it turns out that Nazi Germany was actually never working on an atomic bomb. They spent their time researching things like orangutan super soldiers. Mostly because this stuff was actually brought to Hitler's attention. They're like, dude, we could actually do this. And he was just like, no, we don't care for that Jew science around here. That's, you might think that's racist, but it's Hitler, so come on. Of course it's racist. But literally, like, that stuff wasn't researched because it was considered to be Jewish brand science, which, if you know anything about science, it doesn't matter who does it. Facts are facts. It doesn't matter what religion or creed they are. So as a result, Nazi Germany basically never worked on an atomic bomb.